Welcome back to another deep dive. Today, I want to start with a deception.
Oh, a massive deception.
Yeah, I was looking through the files for this week, and I saw this name, Gallium Monoiodide. And my brain immediately went, okay, simple.
Right. It sounds incredibly straightforward, doesn't it?
Exactly. You picture the periodic table, you take one atom of gallium, one atom of iodine, you stick them together, done. A nice, clean one-to-one relationship.
That's what you would think.
But then I started reading the actual research, and, well, it's a lie.
It is a total lie. If you walked into a lab expecting a simple one-to-one molecule, you would be completely unprepared for what's actually in that jar. This isn't some polite chemical compound. It's chaotic, it's confusing, and quite frankly, it's a bit of a shapeshifter.
That's the exact vibe I got. We aren't talking about table salt here. For those of you listening, we are talking about a pale green powder that has a serious identity crisis. It doesn't even seem to know what charge it wants to be.
No, it really doesn't.
And it's synthesized by literally screaming at liquid metal. Plus, it turns out, the version of this stuff that chemists used for 20 years was actually a mistake.
A mistake that ended up unlocking entire new fields of inorganic chemistry, though.
Right. So that is our mission today. We're going to unpack the wild story of gallium monoiodide. We're going to look at how a messy, incomplete reaction turned out to be this master key for everything from creating chemical sandwiches to bonding with gold.
And honestly, I think it's a great lesson for everyone and why perfect science isn't always the best science.
Let's start with that identity crisis. The empirical formula on paper is Ji, sometimes written as J4I4.
Yeah.
But you're telling me that if I zoom in on this powder, I'm not seeing Gallium molecules lined up like soldiers.
Not even close. If you could shrink down and walk through that pale green powder, you'd basically be walking through a mosh pit. It's a mix, a complete chemical soup.
A mosh pit. I love that.
Yeah, you have gallium atoms that have lost electrons standing right next to neutral gallium metal that hasn't reacted at all. And then there are these big, complex clusters of gallium and iodine all tangled together.
So it's not uniform at all.
No. We call it mixed-valent. Usually in a standard salt, the metal picks a lane, right? It's +1 or it's +2.
Right.
Here, gallium is doing everything at once. You've got oxidation states of 0, +1, +2, and +3, all just hanging out in the same solid.
It's juggling electrons.
Precisely. And that juggling act is exactly what makes it so reactive. It's inherently unstable. It desperately wants to do something.
And it's high maintenance, apparently. The notes say you can't just leave this stuff sitting out on the counter.
Oh, absolutely not. It hates moisture. It completely hates air. You have to keep it in a glove box under an inert gas.
Wow.
And even then, if you want it to last more than a few months, say up to a year, you're storing it in a freezer at -35 degrees Celsius. It's a very fragile chaos.
I want to talk about how this chaos is actually made, because the origin story is fantastic. This goes back to 1990 and a chemist named Malcolm Green, and the method is called ultrasonication, which sounds like a superhero power.
The green synthesis.
Yeah.
It completely changed the game. Before this, trying to get gallium into these low oxidation states was an absolute nightmare. We're talking high temperatures, dangerous chemicals. But Green had a completely different idea.
He took liquid gallium metal, which is already cool because it melts in your hand.
Like the T-1000 from Terminator?
Yes, exactly like the T-1000. So he takes this liquid metal, mixes it with iodine in toluene, which is just a solvent, and then hits it with ultrasound waves.
Intense sound waves. It's a process called acoustic cavitation.
Okay, what does that actually do?
Well, the sound waves create these microscopic bubbles in the liquid that expand and then collapse incredibly violently. When they collapse, they generate massive amounts of localized heat and pressure. It basically shreds the metal surface and forces it to react with the iodine.
So he just screamed at the metal until it turned into a green powder.
In a manner of speaking, yeah, he did.
But here's the twist, and this is the part that blows my mind. For over 20 years, people used this method. They made the green powder, they used it in reactions, but nobody really knew what it was.
That is the big detective story here. From 1990 until around 2012 or 2014, it was basically a black box.
Right.
Chemists knew if you threw this gallium monoiodide into a pot, it did really cool things. But they didn't have a clear picture of the molecular structure.
And it turns out the confusion came from the cooking time.
Right. It wasn't until fairly recently that scientists realized there were actually two different versions of the powder depending on how long you blasted it. There was the incomplete reaction and the complete reaction.
Okay, so walk me through this. The incomplete one is the one everyone was using.
Yes. If you stop the sonication early, you get that messy soup we talked about earlier. Structurally, it's two neutral gallium atoms, a gallium plus one cation, and a gallium iodine complex all mashed together. Chunks of unreacted metal, some ions. It's chemically dirty.
But if you leave the sound on for too long...
If you leave the sonication on, or let it sit too long, it converts into something much more organized. The free metal disappears, and it forms a stable, boring crystal structure, a completely reacted mixture.
And the boring one doesn't work as well.
It works differently, but for the really exciting chemistry, no. The magic was entirely in the mess.
That's fascinating.
Yeah, the unreacted gallium metal in the incomplete version was actually crucial for driving a lot of the reactions people were discovering.
That is profound. If they had done the experiment perfectly, if they had reacted at 100%, they would have missed the discovery entirely.
Exactly. Laziness, or perhaps just impatience, was the secret ingredient.
So we have this green powder. It's messy. It's weird. How do we even know all this? The notes mention Raman spectroscopy and NMR.
Right, and powder X-ray diffraction. That's how they finally cracked the case. By using these advanced characterization techniques, they could finally see the difference between the messy soup and the fully cooked, boring crystal.
So what do we actually do with the messy soup? Because you mentioned it's a shapeshifter.
It acts as a gateway. Because it's so unstable, it is desperate to stabilize itself. It's always looking for partners. In chemistry terms, it behaves as a precursor, a Lewis acid, meaning it accepts electrons, and a reducing agent, meaning it gives them away.
It's a giver and a taker.
It's whatever this situation demands. And its favorite dance partners are things called Lewis bases. These are molecules with a pair of electrons just waiting to be shared. Things like phosphines, ethers, or amines.
But it's not a gentle dance, right? I was reading about something called disproportionation, which sounds less like a dance and more like a messy divorce.
That's actually a really good analogy. When gallium meets some of these bases, the gallium atoms look at each other and say, this isn't working, so they split.
A chemical divorce.
Right. Some of the gallium grabs all the electrons and turns back into a plain old neutral metal message. It just precipitates right out of the solution. The other gallium atoms get oxidized. They lose electrons and form a higher charged complex with the base.
So it sacrifices part of itself to upgrade the rest.
Exactly. It sheds its skin. You see metal falling out of the solution, and what's left is a new, stable molecule.
There was a specific example of this in the notes that I loved, a showdown between phosphorus and antimony. I feel like antimony is the underdog of the periodic table. We never talk about it.
Oh, it plays a starring role right here. This experiment perfectly highlights how aggressive Gai can be.
So round one, triphenylphosphine. This is phosphorus connected to 3 carbon rings. Gai meets it. What happens?
Nothing too dramatic. They shake hands. The phosphorus shares its electrons, and you get a standard gallium-3 complex. The gallium's happy. The phosphorus is happy. It's just a normal coordination complex.
Okay, round two. Swap the phosphorus for antimony, triphenylstibine. Antimony is just one step down on the periodic table. It should be similar, right?
You would think so. But antimony is bigger, and it's softer. And its grip on those carbon rings is a lot weaker because the SBC bond isn't as strong as the PC bond.
Okay.
So when Gai meets the antimony compound, it doesn't just want to hold hands. It turns into a thief.
It steals the carbon rings.
It effectively robs the antimony. The gallium acts as a powerful reducing agent, breaks the bond between the antimony and the carbon, and just takes a phenyl group for itself.
That is wild. It went from a polite handshake to Grand Theft Auto just because we moved one row down the periodic table.
That's the power of the green powder. It can manipulate bonds that other compounds just can't touch. And we see this in the structural details too. If you react it with bipyridine, you get a distorted octahedral geometry where the gallium-nitrogen bond is exactly 2.063 angstroms.
Very precise.
But if you use phenylterpyridine, it twists into a distorted trigonal bipyramidal shape. It constantly adapts its geometry based on what it's reacting with.
Speaking of adapting and manipulating bonds, let's talk about the welder. The notes mention something called reductive coupling.
Oh, this is a holy grail type of reaction in chemistry.
Because usually making carbon connect to another carbon is really hard, right?
It's the absolute foundation of organic synthesis, but it's not always easy. Here, you take 2 separate molecules, specifically immunosubstituted pyridines, if you want the technical term. Got it.
The gallium sits in the middle and literally welds them together. It acts as a reducing agent to form a brand new carbon-carbon bond between them.
So it's not just reacting, it's building.
Yes, it's acting as a template. It pulls the pieces together, facilitates the electron transfer to make the connection, and stabilizes the result.
Okay, so it's a thief, it's a welder. Now, I want to talk about how it plays dress-up. because apparently gallium monoiodide likes to hide inside rings.
Ah, gallium heterocycles. This is where we start substituting gallium into structures where it doesn't normally belong at all.
Usually rings are made of carbon, maybe some nitrogen.
Right, but we can swap gallium in there. They use things like diazabutadines. And the weird thing is how the size of the other atoms changes the result. It's all about steric hindrance.
So steric hindrance is just a fancy way of saying too fat to fit, right?
Essentially, yes. Imagine the gallium is trying to hold hands with another gallium. If the chemical groups attached to it are wearing giant puffy coats, big, bulky groups, the galliums can't get close enough to bond.
So they stay separate.
Monomers.
Exactly. But if they take the coats off, meaning the groups are smaller and less sterically hindering, the galliums can get close, and they bond together to form a pair, a dimer.
But here's the spooky part that you guys found. They looked at these rings with EPR spectroscopy, which basically detects magnets, and they found a paramagnetic anomaly.
Yes, the zombie electron moment.
Explain that to me. What's a zombie electron?
So in stable molecules, electrons are usually paired up. One spins up, one spins down. They cancel each other out. It's quiet chemically. But in some of these gallium rings, the EPR picked up a distinct signal. It found unpaired electrons.
So the electrons are just spinning on their own?
Yes, the molecule is a paramagnetic monoanion. It's acting like a radical, even though it looks like it should be a neutral, stable ligand. It tells us that the electronic structure of these things is way more complex than just drawing lines on a piece of paper.
It's breaking the rules again. It's accessing states that shouldn't really be accessible.
It loves breaking rules. And that's why it's so useful for making N-heterocyclic carbene analogs. Right. NHCs are hugely important in catalysis. GAI allows us to create heavier gallium analogs of these carbenes that were previously almost impossible to make. It opens up entirely new coordination chemistry.
Okay, let's move to my favorite visual in the whole file, the sandwich. Or I guess the half sandwich.
Ah, the cyclopentadienyl complexes, an absolute staple of organometallic chemistry.
Picture a flat ring of carbon atoms for a second, like a slice of bread, and then you drop a metal atom right in the center, just hovering above it.
That's the half sandwich.
Okay.
And gallium is excellent at this. It puts on this carbon ring like a hat.
And there are two main sizes of hats.
Right. You have the standard hat, Gazy, just the basic ring in the gallium, and then you have the star version, Gacy star.
The star makes it sound fancy.
It's definitely fancier. It's the supersized version. It's a pentamethyl cyclopentadienyl ring. Every single hydrogen on the normal ring is replaced with a methyl group. It's big, it's bulky, and it pushes a lot of electrons toward the metal.
So we have the polite small hat, the CP, and the big, aggressive, bulky hat, the CEP star. Let's see how these compare to transition metals. The notes talk about chromium and cobalt. Let's start with chromium.
So if you take the small one, gang P, and react it with a chromium carbonyl complex, the gallium attaches directly to the chromium.
And what does that do?
It triggers the trans effect. The bond on the complete opposite side of the chromium atom actually gets shorter. It contracts.
That proves the gallium ligand is strongly influencing the geometry of the entire molecule from across the room.
Exactly. But the cobalt example is where it gets really wild. We call it the cobalt divergence. This is one of the clearest examples of how size matters in chemistry.
So the setup is the same. You have a cobalt complex, it's happy. You introduce the gallium half sandwiches.
First, you send in the big one, the GAMP star. It's huge. It approaches the cobalt complex, but it's too big to do anything drastic. So it just nudges a bridging carbon monoxide molecule out of the way and takes its place.
It just bridges the gap.
Yeah.
Very gentlemanly. Now the little guy, the standard GAKP.
The little guy has absolutely no chill. Because it's smaller, it can get right in there. It performs an oxidative addition.
Which is what, exactly?
Think of it as a bear hug that turns into a tackle. It completely breaks the bond between the two cobalt atoms and inserts itself right into the middle of the structure. It interacts with both cobalt units and changes their oxidation state.
It fundamentally rewires the molecule.
Completely. The big, scary-looking molecule was gentle, and the small, unassuming one was the home invader.
The lack of bulk allowed it to get close enough to wreak havoc. It really is a shapeshifter. It changes its behavior entirely based on what it's wearing.
It does.
But we haven't even reached the final form yet. We've done sandwiches. Now we have to talk about skyscrapers, the clusters.
This is where we leave simple molecules behind and start building real architecture. We are talking about giant clusters of 9, 10, even more gallium atoms.
The notes mention a specific Gannine cluster, and the shape sounds impossible, a pentagonal bipyramid.
Picture a diamond shape, but with 5 sides around the middle equator instead of 4. It's a beautiful geometric solid made almost entirely of gallium.
And it has these weird outer attachments, too.
Yes, it's surrounded by 6 massive silly groups. Specifically, silicon atoms attached to 3 trimethylsil groups each. But the math on the gallium atoms doesn't add up.
Right. If you try to calculate the oxidation state, you get something like 0.56. That's not a real number in chemistry class.
It's an average. It tells us that the electrons are highly delocalized. They're smeared out over the whole skeleton of the cluster. It's acting less like a molecule and more like a tiny, tiny chunk of bulk metal. It's a metalloid cluster. And you notice there are only 6 silly groups protecting 9 gallium atoms. Fewer attachments than corners. Highly unusual.
And then there's the cobalt cubane, which sounds like a specialized cigar, but I know it's a shape.
It's a cube. Well, mostly a cube. Imagine a sugar cube made of atoms, cobalt, and gallium alternating at the corners. Now just rip one corner off.
That's the shape.
That's the shape. It's called a nider-type cluster, like a nest. But the mind-bending part isn't the shape. It's what holds it together.
Because usually atoms in a cluster are bonded to their neighbors. You'd expect the gallium atoms to be holding hands with the other gallium atoms.
Right. But when they ran the complex computer simulations, specifically Q-tame analysis for the structural nerds out there, they found absolutely nothing between the galliums.
No bonds?
0 gallium-gallium bonds. The galliums are tightly bonded to the cobalt atoms, but they are completely ignoring each other.
So it's a ghost structure. It looks like a solid block, but the internal horizontal supports are missing.
It's held together entirely by the transition metal interactions. The cobalt is doing all the heavy lifting, keeping these gallium atoms locked in formation.
That is bizarre. And finally, we have to talk about the bling. Because apparently our messy groom powder can even bond with gold.
This was a huge deal in the field. For a long time, a true, crystallographically confirmed gallium-gold bond was mostly theoretical. But Gray made it happen.
What does a gold cluster even look like?
In this specific case, it was a triangle of 3 gold atoms, surrounded by these gallium ligands protecting them like bodyguards.
And are they sharing electrons nicely?
That's the interesting part. It completely depends on where the gallium is standing. If the gallium is just attached to one single gold atom, the bond is super polarized. It's a very unequal relationship. There's a big charge difference, and the gallium is basically throwing electron density at the gold.
But if it bridges?
If the gallium sits right between 2 gold atoms, holding on to both, the bond becomes much more covalent, more sharing. It becomes more like a true partnership.
So even with gold, gallium is adapting. It says, if I'm here, I act this way. If I'm there, I act that way.
Exactly. It creates polarity where you need reactivity, and it creates covalency where you need stability. It is the ultimate chemical diplomat.
So let's zoom out for you guys listening. We started with a scientist screaming at liquid metal in 1990 to make a pale green powder.
A powder that everyone thought was a simple one-to-one salt, but turned out to be a chaotic mixture of everything at once.
We learned that this mistake, this incomplete reaction, was actually the secret weapon all along. It allowed chemists to steal carbon rings from antimony, weld molecules together, build sandwiches that break cobalt bonds, and construct massive clusters with weird math.
It really challenges the way we think about purity in science. In school, you're taught that pure is good, impure is bad. But here, the impurity was the actual engine of discovery. The unreacted metal, the mixed valence, states that chaotic energy drove the chemistry.
It makes me wonder about all the other failed experiments sitting in lab notebooks right now.
Oh, absolutely. Think about how many times a graduate student has thrown away a weird gunk or a sludge because it wasn't the beautiful pure crystal they were looking for.
When the sludge might have been a massive breakthrough, gallium monoiodide teaches us to look closer at the mess.
It does.
Because if a simple mix of gallium and iodine can hide this much complexity for over 20 years, imagine what other simple compounds sitting on a shelf right now are actually misunderstood treasure troves of reactivity.
Never throw away the sledge.
Never throw away the sledge. That's a terrifying and exciting thought for anyone working in a lab today. Thanks for diving deep with us into the weird, chaotic world of gallium monoiodide.
Always a pleasure to be here.
We'll catch you on the next deep dive. Stay curious.